Hi, everyone. Thanks for joining us for our webinar. Just so you know, this is being recorded and it will be available on YouTube in the next few days. And we also have some expert panelists from D-Wave to answer your questions. So if you have questions throughout the webinar, please feel free to use the Q&A box and we will do our best to get to your questions. Now I'm going to hand it off to Nikhil and he's going to introduce our speakers today.
Thank you, Sarah. Good morning. My name is Nikhil Dhingra. I'm Director of Product Marketing here at D-Wave. Thank you, everyone, for joining. We have an exciting show today and topic. We've got Mark Johnson, our Vice President of Quantum Technologies and Systems Products, and Murray Tom, our Vice President of Product Management here at D-Wave. Mark has been involved in development and commercialization of technology for nearly 25 years. Mark leads the R&D and quantum hardware programs here. Mark joined D-Wave in 2005 as an experimental physicist and superconducting circuit design engineer to help develop, build, and deliver the world's first commercially available quantum computer. He continued to work with the D-Wave team to develop and release subsequent generations of quantum computers. Most recently, Mark led the development and delivery of the company's 5th generation and most powerful and connected commercial quantum computing system ever built, the Advantage system. And you'll hear about that more today, the performance update there. Murray is Vice President of Product Management here at D-Wave with nearly 20 years of experience in the quantum computing industry. In previous roles at D-Wave, he was responsible for the development and delivery of the Leap quantum cloud service and the Ocean open source tools. He's led teams engaged in customer projects related to algorithms, applications, and performance testing. He's even assembled a few early quantum computers by hand. So welcome them both. Thanks for joining. And over to you, Mark.
Okay, thanks, Nikhil, and good morning, folks. I think it was just about a year ago that I was with Murray here at giving a webinar and telling maybe some of you folks about Advantage, our 5th generation quantum computing system, which was really designed from the ground up for business. But while Murray and I were talking to you about that, our colleagues were already hard at work on what's coming up next. So I'm here this morning to share with you what we've been up to and where we're headed. We recently gave a sort of a look into our roadmap at our Qubits user group conference. So we're going to be taking another look at that here, but I'd also like to encourage you to go and check out some of the other talks from Qubits online. We'll be telling you more about how to do that coming up at the end of the webinar. I just want to give you a high-level view of what's coming up this morning's discussion. I'm going to dive into our quantum technology and systems part of the business. And then Murray's going to be talking to you about our software tools and service. So, D-Wave is a full stack quantum computing company. So it won't come as a surprise to you that we have a full stack roadmap. So at a high level, I'm going to start this morning by reviewing our quantum annealing roadmap. We announced earlier this month, actually, that D-Wave has begun work on a program to develop a gate model quantum computer. And so I'm also going to be talking to you about what's coming up there. A little later, Murray's going to give you a preview of our new hybrid solvers and where we're headed with Leap, our quantum cloud service, and then also with the Ocean developer tools. And this is going to include new classes of hybrid solvers, and then also talking about cross-platform open source tools for both annealing and gate model quantum computing. So when we started all this some time ago, we thought that quantum annealing would provide the most direct path to valuable, practical quantum applications. And this has proved true. We've delivered 5 generations now of progressively more powerful quantum annealing systems. Our customers, maybe some of you, have built more than 250 early applications for real-world problems using our systems and technologies, things like protein folding, manufacturing process management, retail optimization, to name just a few of them. But we now understand from a growing body of published theoretical work that quantum annealing will always be more effective than gate model quantum computing for optimization problems. And this is a large share of the addressable market for quantum applications. So our roadmap is always going to feature a series of progressively more powerful quantum annealing systems. So last year we introduced Advantage. A couple of weeks ago, we announced the release and general availability of Advantage Performance Update, where improvements in design and fabrication are going to allow us to deliver customers better answers faster. And I'm going to talk to you about this in more detail in a little bit. Up next, we're already hard at work on Advantage 2, which was going to incorporate an important innovation in a qubit design that's going to enable us to get up to 20-way connectivity and implement a new topology. The Advantage 2 QPU is going to be implemented in a completely new multi-layer fabrication stack that we're rebuilding from the ground up for increased qubit coherence. Beyond Advantage 2, we see a continued emphasis and focus on improving qubit coherence to deliver both better performance in quantum annealing, but also to enable, in turn, progressively greater increases in interqubit connectivity. And so going forward, a continued focus on qubit coherence, connectivity, and of course, qubit count, we feel is going to pave the way towards a series of progressively more powerful quantum annealing systems going into the future, and ultimately around delivering better performance on existing quantum applications, but also importantly, opening the doors to new ones. So while we know that quantum annealing is always going to be the most effective approach to solving optimization problems, which is a big part of the addressable market, we do also understand that there are some important business problems, and for example, in quantum chemistry, that are going to be better addressed with a gate model architecture. And we want to be able to bring value to our customers across as much of the quantum application space as we can. So we announced this month that D-Wave has begun work on a program to develop a gate model quantum computer. We realize that many of the challenges we've struggled with and overcome over the more than the last decade and a half of developing, delivering, making available quantum annealing systems really positions us well. There's a good foundation for us to do this with the gate model quantum computer. And we believe the only practical, scalable approach to do this is to build it using an integrated multi-layer superconducting fab stack. This has been the cornerstone of our technology to date. And we think work on quantum annealing and gate model systems together is going to be synergistic. So going forward, our roadmap was going to continue to feature development along these two synergistic threads of quantum computing architecture. So let's take a closer look at what's coming up in each. So the Advantage Performance Update was released a couple of weeks ago and is available right now in Leap. So innovations in design, materials, fabrication process tolerances are paying off here with much higher qubit yield, which ultimately translates into us being able to address larger and more complex problems. Improved dynamic range and precision in specifying problem parameters help out in giving better quality solutions. And with the performance update, significantly faster anneal times are possible now than have been in any previous systems. And this helps out with some quantum simulation applications. All this boils down to getting higher quality answers on larger, more complex problems faster. If you'd like to hear more details about what we're seeing with the performance update, I'd encourage you to come check out a talk that my colleague Kathy McHugh gave at the Qubits user group meeting. I alluded to that earlier. And she gives a nice sort of overview of all the performance benefits we're seeing, but just a couple of specific examples. For 3D lattice problems with the performance update, we're getting optimal solutions twice as fast as with the original release of Advantage last year. And on not all equal 3-set problems, which is a hard class of satisfiability problems, the Advantage Performance Update basically beats or draws the original release 97% of the time, winning 57% of the time or more. So a significant and quantifiable boost in performance. So I'd like to make a point here. Each one of the 5,000 qubits in this system is connected to 15 other qubits, but you can still pose problems directly to the processor where a variable may be influenced by or interact with more than 15 other variables. For example, you can take 2 qubits, couple them together, treat it as a single logical qubit or variable, which can be connected to almost 30 other variables, and so on. And this is part of a process called embedding that allows us to, among other things, trade off physical qubits for connectivity, and in general allows us to pose very complex problems directly onto the processor. Now, by the way, we have really excellent software that will do and handle this embedding for you in the Ocean suite of tools, and this is how I go about it. But I want to consider the most extreme example of this process that I can conceive of, which is a problem so interconnected that every variable in the problem is connected to every other variable, represented by what computer scientists refer to as a fully connected graph or a complete graph. And I'd like to ask a question, which is, what is the largest complete graph that I can embed in this advantage system? So I'm showing here front and center on the chart a graphical representation of a complete graph of size 177. And this is the largest size that we can embed with the performance update. And I'd like to put that into the context of all the previous quantum computers that we've developed and delivered to date. So I'd like to do that with this chart, this graph that I'm going to explain to you. I'm showing this here on a new plot. On the y-axis, I'm showing the largest complete graph sizes we've attained with each quantum annealing system that's been deployed and provisioned and delivered over the years. And on the x-axis, I'm showing the time that system was delivered. So for example, with the D-Wave 1, the first commercially available quantum computer, could embed complete graphs of size 16 or up to size 16. 2000Q up to 64. Advantage, released last year, was 117. With the performance update today, this brings us up to 177. And this last jump in size was paid for completely with improved qubit yield. So the y-axis is on a log scale. And so looking at this, stepping back and looking at this over time, you see that the complete graph size that we're able to embed appears to be growing exponentially in time. But if we reflect on this a little bit more carefully, we see there's something else going on here, which is the complexity or difficulty of dealing with problems encoded in this way is increasing exponentially in the number of variables of that problem. So in an important way, this chart is showing us an exponential on top of another exponential. And by the way, I want to emphasize something here. With our hybrid solvers, we can pose and solve problems with up to 1 million variables, where the hybrid solver will choose the best way to call the QPU given the problem that you've posed. And for most applications, this is almost certainly the best way of using the technology. But what I'm talking about here, what I'm discussing here, is really an under the hood QPU level metric. And I like this way of comparing processors of different sort of generations for a couple of reasons. One, it's agnostic to topology, which makes it easier to give you a fair comparison between things that are designed very differently. But in another point is that it's much closer to the problem space. And so I think it's more useful for you than me telling you how many devices I have on the chip. So this gives us a way of visualizing the progression of our performance over time. And we think about it in these terms and see this continuing. So up next, sort of featured on the right-hand part of this chart, is going to be Advantage 2. And the team's already been hard at work on this. So powered by an important innovation in qubit design, this is going to be a 7,000 plus qubit processor, which will be implemented in a new topology, degree 20 connectivity. And by the way, you can find a link to a really nice write-up on the details of the new topology. I think in our press release that came out at the beginning of the month, there's a link to it in that. This new processor is going to be implemented in a completely revised fabrication stack, rebuilt from the ground up with a focus on improving qubit coherence, but also importantly, paving the way towards future improvements in coherence going forward. And this is really all about being able to get better harness the power of quantum mechanics when we're solving problems using quantum annealing. And this ultimately is around driving towards better performance on existing quantum applications and opening the doors to new ones. So after Advantage 2, we really see a clear path towards continued emphasis on improving qubit coherence, improving both to improve performance in quantum annealing, but also enabling further increases in connectivity. And then focusing on these and qubit count going forward, we see will drive us towards progressively more powerful quantum annealing systems. So for us, quantum annealing is here to stay. It's really the best way to solve optimization problems now, and it really appears like it's going to be into the future. And by the way, my colleague Kathy McHugh gave a really nice presentation on why we're so bullish on quantum annealing, which you can see if you go and sign up for the Qubits content that we'll tell you about at the end of the talk. And I'd encourage you to go look at that. She really sort of gives an overview of the current scientific literature and the new findings. So while we're going to continue to focus on our bread and butter of quantum annealing, we do also know that there are business needs for problems, for example, in quantum chemistry, that are better solved with the gate model architecture. And we want to be able to provide solutions for our customers across the whole space of quantum applications. We'd actually like to be able to do this in a platform agnostic way, by which I mean that you can come to the table being an expert in the problem that you want to solve, but not necessarily an expert in knowing which architecture is the best to solve it. We told you, we've mentioned recently that we're developing a gate model quantum computer. So let's take a closer look at our approach. So we've mapped out a phased approach to deliver gate model computing to our customers. Phase 1 is develop our gate model qubit designed from the beginning for scalability, implemented in a multi-layer superconducting integrated circuit stack. And this work is already underway. Phase 2 is validate our approach to error correction and integrated on-chip control and I/O. And this phase is going to target a single scalable logical qubit comprising probably 60 physical qubits. Phase 3, demonstrate our scalable approach to logical qubit manipulations and interactions using the on-chip control. This is a sort of a critical proving point for the roadmap, and we'll target here about 1,000 physical qubit system configurables up to 4 logical qubits. Phase 4, develop task-specific components. So much like the classical digital CPU, a fully functional gate model QPU will be a collection, an assemblage of architecturally distinct task-specific components. Modules for state initialization, logical qubit interactions, state of movement, memory registers, these are all going to be needed. Phase 5, pull all of these together into a general purpose error-corrected QPU. So our 15 plus years track record of innovation, development, delivery of quantum annealing systems is a really strong foundation for developing a working gate model quantum computer. And we believe implementation in a superconducting integrated circuit fabrication stack is the only really feasible, practical, scalable approach to building a quantum computer of either flavor, either architecture, quantum annealing or gate. We'll use our fabrication technology to develop tunable, addressable qubits with efficient, scalable I/O, and avoiding the electromagnetic crosstalk that others do seem to struggle with. And we also have the quantum systems integration experience required to incorporate superconducting technology into delivered products that solve real business problems for our customers. So quantum annealing and gate model together are synergistic for us and complementary for our customers. But we also need to consider, and this is really foundational to our development approach, the big picture of what we're working on together. We think it's not just enough to build the systems. We also have to be paying attention to how our customers are using it and how to deliver it to you and how to help you solve the important business problems that you have. So we think it's as a full stack provider, we believe strongly that co-development of the physical technology along with the software is essential. So while I've been talking to you about Advantage, we also are going to be talking to you, Murray's going to be talking to you about our Ocean suite of tools, developer tools, our quantum cloud service, and our services model. So with that, I think I'm going to turn it over to Murray.
Terrific, Mark. Thanks very much. And I'll share my screen. Can you just confirm for me that you see my screen okay?
Yep, looking good.
Perfect. Terrific, everyone. Well, thanks for joining us this morning. And I'm really excited to be talking to you about Leap and Ocean and how they're going to be building and growing through the Clarity roadmap. And really, one of the patterns or the threads I want to kind of pull through here is that all the work we're doing in these products is about allowing you to focus on your business problems and demonstrations of business value. So whether that's involves you doing a problem in terms of like increasing efficiency in your business and being able to operate more efficiently, you want to be able to build that application and run it in a matter of weeks or months so that you can build the case internally about how quantum computing is going to expand the business opportunities in your area of work. If you're a researcher, we want to be able to bring some of the power of the new technology forward to you, make them more programmable so that you can actually really push the boundaries of testing quantum annealers and what their capabilities are. And if you're a developer, we want to make this really much easier to learn, much more designed for your professional work environment in terms of like searching up open source code examples, being able to build off of those, search for them based on the kinds of techniques that are applied, so that you can really build rapidly and get those new ideas incorporated. Solve your traditional business problems, but in new ways using this new technology. Right. So what are some of the key elements here that are really at play as we're designing this Clarity roadmap? Well, one is, the Qubits user group meeting, these webinars, the questions that you're asking in the Q&A, that's all providing us with customer feedback that is really important for us in terms of what are the core challenges that you have in putting the technology into application, and what are the opportunities, what are the things that you need most from us next, so that we're designing based on that feedback. And our professional services team, which is working with many of you as well as other customers, are also really working on that challenge of formulating problems for hybrid quantum classical computing and direct quantum programming, so that we can learn the kind of design patterns and actually begin to bring that forward to you so that it's faster and easier to build. We're also focusing on all the lessons about bringing forward a production application, stability, infrastructure, support, security, and really leveling up there all across our business to make sure that we're meeting your needs as you're looking to run production applications. And we're also keeping a really close eye on the marketplace, what's happening in quantum computing and optimization more broadly, and cloud computing, to make sure that we're bringing forward the best technology as quickly as possible for the work you're doing. And we're hoping that you're going to find that that gives you the opportunity to really innovate in your business and solve some new problems in creative ways, interact with some of your peers, and look at applying new techniques and learning to your problems. So some of you might know this, and some of you might not, that our world-leading Advantage quantum computers are basically online right now with 5,000 qubits and 15-way connectivity that Mark was talking about, and you can get access to them immediately. So you can program them, and when I say immediate, I mean in the cloud, you can sign up in minutes and begin programming demos and see a response from the quantum computers in seconds. You don't have to wait until later in the week. You don't have to pre-schedule a time at some other period to program the quantum computers. And that real-time access is really important in terms of learning and building quickly, because quantum computers are different than classical computers. And we need to be able to interact with them if we're going to learn the lessons that we need to be able to use them effectively in production applications. And we're trying to bring forward through our user interface a rich set of resources, learning resources and programming resources We're trying to bring forward all the tools from the Ocean SDK, which is open source in GitHub, but also present those in a way where you can learn the concepts, search through the open source examples, and get started quickly. And we've also got an integrated developer environment right in Leap so that you can, if you see an interesting idea, if you want to explore some of the ideas that you're seeing through the documentation or through the code, you can load it right there in seconds so that you can start programming and you don't have to worry about setting up a local environment until after you've had a chance to explore things and really begin to build and prototype. All right, so I'm going to be talking about these areas of the Clarity roadmap, the Leap Quantum Cloud and the Ocean Developer Tools, and sort of really bringing forward how we want to help enable you to apply those to application domains now and in the coming years so that you can sort of see the direction that we're taking, and also so that we can get your feedback about that direction and make sure that it's really taking into account exactly what you need when you're looking to apply the technology. There's three principal components I'm going to be talking about here over these sort of sets of years through the end of 2021 out into 2024 and beyond. One component is powerful hybrid solvers. So these are available to you in Leap, and they are combining the best of quantum and classical technology to those problems to allow you to get results quickly. Also, cross-platform open source tools. This is about helping you to solve problems as close as possible to the way that they're natively expressed, as close to how you see them in the application domain, and making that fast and easy to build with sort of professional tools and searchable examples so that you can basically pull together building blocks, leverage the work that's happening in the community so that you can see results quickly. And as we're broadening out into gate model and expanding from annealing to include annealing and gate model, we're going to basically build on that platform to make it really simple for you to see, what applications are suitable for what technology. In that case, it's not technology led. It's not about, let's look at the technology. Okay, now what are we going to do? Because in your lives, you have problems, you have challenges that you're facing, and it's really, you want to solve that problem, and whatever technology is most suitable, you want to see it applied. That's the way you're going to see it integrated through those cross-platform tools. And the other thing is we're doing a lot of enhancements to the Leap Quantum Cloud service in order to make sure that we're meeting all of the needs that you have as you're taking quantum exploration out into production. And we have many customers that we're working with right now who are actually able to program the quantum computer in days, get results that they can use to assess business value, and actually write papers or begin to use it in production in the field within months, which is really exciting. So that kind of transformation is possible for all of you as you get exploring the systems. Okay, so let's dive in a little bit more about the powerful hybrid solvers. So by hybrid solvers, what do I mean? I don't mean an emulator of the quantum computer. This isn't about studying the quantum computer better. We have a lot of that work in research papers. This is about helping you get results in production applications quickly. So this is enabling you to express problems at full application scale. So the first example here, the binary quadratic model solver, accepts very much the same problem form as the quantum processors themselves, but allows you to pass in as many as 1 million variables so that you can get to enterprise scale quickly. And it works across that with resources in the cloud, breaking pieces out of that problem to submit them to the quantum computer, and then reincorporating those answers from the quantum computer into the solution. Now, if this is something that you want to do yourself, we have a D-Wave hybrid open source framework to allow you to do that algorithm design. But for many of you who are trying to solve application problems in business or out in the commercial world, you need the results really quickly. This allows you to get to those results quickly like that. Now, the next thing is we really learned that binary quadratic model solvers and the way that the quantum processors are contributing to a hybrid algorithm actually affects a wider array of problems. So we've also enabled a discrete quadratic model solver, which allows you to express options like option optimization. So choices between 11, 19, and 29 that don't normally fit into binary variables. And that allows you to get to another class of application problem more easily. But with this announcement, we're introducing the constrained quadratic model solver. And this is really the result of having listened to you and worked with you, many of you, on applications, which is that real world applications in so many cases involve expressions of constraints, which is the maximum weight this vehicle can handle is so many tons. The maximum number of shifts that this particular employee can work is so many hours. And so this allows you to express those constraints natively and hand them into the processor. That's going to give you a whole lot of new capabilities. One is that it's going to be faster to actually formulate your problems for the system, because you're going to indicate, this is the objective I'm trying to reach. This is how I weight choices in the optimization that I'm trying to accomplish. And then separately, and here are the things that must be satisfied for the solution to work for me. And if it's outside of this domain, I won't be able to work with them. And the solver can then hand you back whether it was able to find solutions in that feasible space or in the infeasible space, which is an important piece of information as you're quickly evaluating solutions. So this is going to allow you to work with integer variables as well as binary and the discrete that I was discussing earlier. It's also crucially going to allow you to introduce quadratic terms. So moving out of the linear space into the nonlinear, and work up to 100,000 constraints, which are either inequality or equality constraints. So the key for native representation is that it's faster to formulate the problems. The problem expressions themselves are more compact. So you're not moving around as much data because it's expressed in a more compact way. And the algorithms that are working on creating solutions for you, the hybrid algorithms, are able to do a better job because they're seeing the truer representation of the problem as it's seen sort of in the real world. So as we're looking at the clarity roadmap and what that's going to mean over the coming years, here is the feature of these hybrid solver services that are available in Leap, which is that we have a program running all the time across our entire technology stack, improving those hybrid algorithms. So any approach in terms of making better hybrid moves or making better performance tuning of the processor as it's contributing to those hybrid moves, or finding complementary classical algorithms that can contribute to what the quantum processor is doing, those are all compounding benefits that are going to appear as the versions of those hybrid solvers are upgrading. As well, as we have new quantum processors come out, the Advantage system, the Advantage performance update that's just been released, as we're going towards Advantage 2, we're making sure that those hybrid algorithms are designed to incorporate that best technology the moment that it's released. And that's exactly what we've heard from you out in the real world in terms of what you need in your applications, which is excellent backwards compatibility, excellent onboarding of new technologies, just the way that they need to be applied, because that's allowing you to focus on your core business problems. And that combined with our expanding tools and interfaces to allow you to express these problems more natively is crucial, because that's going to allow the solvers to work more efficiently over like the natural description of the problem. And then moving out on the roadmap, we're going to learn from our mutual experiences, the experiences of the community and our experiences working with business, to see how we can take vertical solvers, so like domain expertise, and sort of say, okay, if we're working on manufacturing floors and we've got machines with certain constraints, we need to deliver materials to those machines within a particular time window. We don't have to abstract that all the way back to ones and zeros or abstract integers. We can start to introduce domain-specific language for those applications, and we're going to really work closely with the community to sort of bring those forward to make, again, increase the rate with which we can get rapid application development with quantum computers. Okay, with that, let me move on to the cross-platform open source tools, because I'm sure that many of you are curious about programming gate model systems, programming quantum annealing systems. I was just on a panel yesterday where some folks were asking me about, the core differences between the technology. And D-Wave is going to take its traditional approach, which we have found it provides the most value for you as the community of users of quantum computers, which is, let's focus on how these technologies can be used in application as quickly as possible. So in the case of annealing quantum computers, it's about optimization problems, Monte Carlo sampling techniques, risk analysis, pricing, logistics, and scheduling optimization in a variety of industries. In gate model, it's about the sets of simulations that you can do with that expanded control, being able to do fermionic simulations for quantum chemistry calculations or drug design, being able to work with differential equations as you're working through applications where you're using that kind of math. And so we're going to use the Ocean tool set and the experiences that we had to use those applications that are closely connected to the technology to drive that usability so that you can start using them in applications as quickly as possible. Next is that we learned some really important lessons as we were building the hybrid solvers, which is that, you're not using computer processors independently because they're your best friends. You're applying them because of what they can do for you. And so as we had, years and years of experience in comparing and contrasting classical computers with what quantum annealers could do, we found actually that they're quite complementary in terms of how they contribute to solution finding in a hybrid solver framework. And so we actually built up the Ocean technology stack, and we found those abstraction layers where the two of them could work effectively together to allow you to solve application problems. That's exactly the same approach we're going to take as we're combining quantum annealers with classical computers and gate model systems. And you're going to see that in the open source examples, which is really application led. If you're looking at this particular application and you want to create a solution for it, here's how that problem gets formulated, and here's how it's used, and here's the solver that gets called. And that's how you'll find, okay, yeah, in this case, a gate model computer is the one that's getting used here. And those abstractions make it much simpler and much more application focused in terms of getting results out of the system. So with that, I'm going to move on here to our next section, which is that it's more than just the details here in terms of our roadmap. It's about giving you a fully threaded set of resources all through LEAP. And for those of you who have been programming quantum annealers all this time, the integrated developer environment, learning resources and documentation that the LEAP community and our support site and our federated search across all those resources, that's really allowed people to level up very quickly in terms of applying quantum annealers and quantum computers into application. And that's what we're going to use over this roadmap going into next year, and then also in 2023 and 2024, to basically pull all those resources together across that set, so that you really have sort of a full set of resources to allow you to attack that full set of application use cases. Okay, so let's talk about enhancements to the LEAP cloud service. And this is really about enabling you to get through the stage where you're learning to the point where you're producing. Your quantum applications would be delivering business value. You can measure it. You can actually give that information to the rest of your team and help them to see how and where the quantum technology is going to be contributing. One of the things that we've heard from the market is that it's really important to simplify and understand benchmarking of quantum computing systems. And we are planning on bringing forward that simplicity and understanding of benchmarking quantum computers through our LEAP service. And as the only provider of real-time access to quantum computers, we feel we're the best to be able to do that. So we're going to bring forward a set of resources this year and next to help make it clearer how to express performance and performance expectations for quantum computers when running them in application, and also trying to bring forward the resources to allow you to have access to that information, dive into the details, and test that out. We've also learned a lot from talking with our customers like yourselves and working with our professional services partners, also like many of you as well, in terms of bringing forward a set of resources to really meet your needs in the application marketplace. So expanding our in-region systems to Europe. It's been announced that we're going to be bringing a system out at Jülich in Germany, and enabling those through our LEAP cloud service, as well as helping you to manage sort of the load and resources in a professional manner through new administrative tools that have now been brought forward to allow you to manage the users on your system and make sure that you can keep track of, do you have the right set of resources? Do you have the right capacity for the applications that you're working on? And bringing that more forward to you so that there's a lot simpler administration of your teams. You can integrate it into your systems and make that go more smoothly. And we're also seeing a lot of early signs of those of you who are really entrepreneurial, who have independent software development practices in place, and you want to get accelerated more quickly. We're learning lessons from that community on how can we bring forward resources to that community to get you started so that you can start delivering applications that are accelerated by quantum hybrid technology and out into the marketplace. And also trying to help you bring forward those solutions and how innovative you're being in terms of bringing those solutions to your customers, so that you can sort of talk to your customers about how you're using quantum technology to open new opportunities for them. And during that longer stage of the Clarity roadmap, we're going to be looking at introducing more in-region systems in more areas. That helps us in terms of making sure we have fewer single points of failure, and allows you to also access the systems using the resources that are close to where your customers are located. So let me talk a little bit about these are the areas that we're really focusing on as we're trying to bring forward the features that you expect and that you need for enterprise level quantum application delivery. And we're absolutely trying to work really closely with you and listen to you in terms of what your needs are, so that we're bringing these capabilities up just in time, so that you can basically work with them and rely on them. I spoke already about expanding our systems in LEAP into different geographies, giving you higher reliability and also more local access to resources. We're also really working on security. Many of you are used to the high quality security of our APIs and interacting with the LEAP system. We're also looking internally to make sure that we have the practices in place to make sure that we have the appropriate auditing, logging, monitoring, to make sure that all of our internal systems are meeting the needs that you would expect for a production application. We've been working for a long time now, since we've expanded our systems around the world on privacy and making sure that we're keeping at the cutting edge of making sure that we're keeping your data secure and private. And we're also doing internal auditing work on compliance. I'm looking at building out our compliance standards so that you can basically run your applications in the professional way that you expect. And we'll also be looking for more ways that we can enhance our administrative features so that your systems operators can work more efficiently with better integration into your enterprise systems, create links between your internal systems and your LEAP cloud environment, just the way you would with any professional cloud provider. And as we're moving forward towards service level agreements, I mean, I am deeply, deeply aware of how important it is to get really high quality support as you're building production applications. So we're doing a lot of work focusing on our ability to deliver high uptime, to be able to manage anything in terms of disaster recovery, to bring you best in class reporting so that you're aware of the status of our systems and can check that and monitor that through your programs. We're also looking at our support hours and looking to make sure that we can find the best ways to provide you the best support at the broadest array of times to meet your needs as you're building out. And then really make sure we have all the internal systems for monitoring and maintaining that, so that we can set and exceed our service level objectives and really give you exactly what you need in your agreements for contracts working on production applications, which is really exciting in quantum computing. So with that, I'm going to leave you with a set of links. You know, I saw some questions about where to find information. So absolutely, if you want to reach out to D-Wave and find out more, please contact sales@dwavesys.com. We've got our D-Wave launch program. So this is for those of you who are really interested in putting quantum computers in application. Maybe you're looking to explore a set of use cases, or maybe you're already programming with quantum computers and you want to increase the efficiency of your program. Or maybe you've actually already built some business use cases, you've prototyped things, you're ready, you want to go into production, and you want to basically accelerate that process. That D-Wave launch program allows you to come in at the level that your team is basically working and get going on launching your production applications. I also saw some great questions about use cases in applications like AI and machine learning, but also you'll find many other application areas. And you can take a look at our applications section on our D-Wave webpage. There's a searchable set of examples there with other resources. Mark alluded to the amazing work that our community has done with over 250 early examples. Many of those are actually linked there with resources in terms of open source code, if there is open source code, the presentations online, or the papers writing up that work. So that's a great place to get started if you want to see some examples of where people are applying this technology, so that you can begin to hone in your own areas to determine where it might be most suitable. We've got a whole set of online resources, white papers and case studies and examples that you can look at. And if you want to get started programming the quantum computers, in the next 10 minutes or after this webinar, before you even have to go for your first coffee break, you'll be able to submit your first problem to a quantum computer and run some demos and learn how optimization with quantum computers works. And also, we just had our Qubits user group meeting. There was an excellent set of presentations. I saw from many of the attendees here, many of you presented at the user group conference. And if you were presenting, or if you were answering questions, or maybe even if you were at work watching the conference, there might have been some things that you missed or that you want to refer back to, you can check out this URL. For those of you who haven't registered, you can register for the conference there and go in and watch the pre-recorded talks. That's an excellent resource. So thank you all for coming and joining us this morning. It's really exciting to work with you. It's really exciting to see what you're doing in terms of applying our quantum computing technology to your business applications. That's why we all get up in the morning at D-Wave, to sort of see what you can do with the technology, and drives us forward so that we can accelerate the technology as quickly as possible to allow you to do your best work. And with that, we'll go to our Q&A questions. So I'll ask Nikhil and Mark maybe to come back. And Nikhil, do you want to highlight some questions for us?
Absolutely. Yeah. And thank you, Mark and Murray. Great stuff. And again, thank you everyone for your great questions. There were a lot of good questions and engagement, and we're going to try to answer a handful of them today. Olivier asked some great questions. I'm going to pass those over to Mark to kick it off.
Yeah, those really, really interesting questions, Olivier. So definitely with gate model systems, RF and microwave signals are needed to be able to control them. And so that's going to be part of the control schema. As far as RSFQ, there's actually a much broader array of superconducting-based electronics circuitry sort of approaches outside of RSFQ that are applicable. And so we use a sort of a large portfolio of these to do control of annealing systems, and we see many of the same techniques and control architectures, control circuits map over to gate model. Not all of them. There are some that are definitely unique, but there's a reasonable amount of overlap. I want to make a point about Advantage 2 is very much a quantum annealing. It's a quantum annealing processor. So that will not be a gate model processor, but that of course has its own control system, which handles is able to control the thousands of qubits and tens of thousands of couplers, and manipulate it all with a reasonable number of wires coming up to room temperature. So in terms of the number of qubits for the gate-based systems, it's actually we sketched out a path in our roadmap, and we're looking at sort of starting off with relatively small numbers, focusing on error correction and methodologies, and then working up to larger systems. But that's all spelled out, like for the different stages. You can go to the Clarity roadmap and sort of what we're spelling out for what we're looking at there. For the error correction approach, we'll definitely be using surface code approach for that. More than that, we won't get into, but absolutely for surface code. You actually had it was a really interesting question. Actually, maybe my favorite question is about a single architecture for annealing and gate-based. It opens up a door to a really fascinating possibility of hybrid processors, where you maybe have both architectures or physics associated with both architectures going on at the same time. I'm not gonna rule that out. I think that there may be some really interesting possibilities of that. And then actually just chemical simulations is one example. They're material simulations. Those are ones that have clear. So why, in other words, why are we choosing that as one of the target areas? That's just one of the looking at the space of quantum applications that folks are interested in. Those are areas where there's a need, and it's actually will be and it's important. So these are problems that people want to solve, and they'll look like they're applicable. So and then I wanted to jump over actually, and Deborah Cobley actually asked a really interesting question about the limit to the number of qubits that can be employed. How many qubits can you use? And it will depend on the sort of the generation. I just have to look at that question in the perspective of through the lens of history. When I started at D-Wave, and it was 2005, and my first job was to design a superconducting integrated circuit chip that had 2 qubits coupled together. And we got up to, maybe within a year or two, we got up to 16 qubits. And I don't know that I would have been able to answer that, predict that in 2021 we would be talking about, or 2020 we'd be talking about systems that had 5,000 qubits. We're not, for the annealing roadmap, we understand pretty well we're not anywhere near the limit of what's possible. There will be many engineering advances that are needed to get us to continue the scaling, but that we don't see a physical fundamental limit, and I believe the same thing is going to ultimately be true for gate model architectures. So Nikhil, I don't know if
Great.
there's...
Yeah. No, thank you, Mark. And again, thanks everyone for these questions. We're getting to as many as we can. And we have our, other channels as well, our LEAP community. I encourage you to be active on there, ask questions, and we're always on standby to answer, as well as others in the community. We've got one question from Rolf for Mark. Are flex qubits easier to error correct than other types of qubits?
Oh yeah, Rolf, that's actually a great question, and it allows me to sort of point out something. I didn't emphasize this in the presentation, but our approach to gate model is going to feature a flex-based qubit. So it certainly will not be the same flex qubit that we're using for our quantum annealing architecture, but it's flex-based, and ultimately the reason we chose that is because at a sort of at the system level, a combination of, how do we error correct? How do we do control of it? Scalable control, et cetera. That it's overall the best choice for scalability.
Thank you, Mark. A couple others, and Mark, and feel free to jump in if you had some that you saw you wanted to answer. One is around, so Advantage 2 represents a smaller increase in qubit capacity from Advantage than previous new hardware did over similar timeframes. Should we expect smaller percentage increase in qubit capacities per generation going forward? That's from Jerry, and I'll pass it to Mark.
Yeah, that's Jerry. That's a really important question. I want to go back to that. The chart that I showed, where we are looking at progressively larger complete graphs that are embeddable. What we've learned, and initially when we were starting out, we were focused on qubit count. But I think what we learned as we understood better and better how to apply real world problems onto the processor is that yes, more qubits is helpful, but actually it's maybe more efficient to increase the number of couplers in terms of being able to solve larger, more complex problems. If you go back to 2000Q, our D-Wave 2000Q, we could solve cliques of up to, fully connected graphs, complete graphs of up to maybe 64. And then with the recent performance update, we're up to 177. So that's sort of a 3x increase, but without a 3x increase in the number of qubits. So that's just by more connectivity. So I think the concern more is on what can we do to improve connectivity. And then what can we do to improve coherence?
Nikhil and Mark, can I jump into, because one of the things I'm noticing is a bit of a pattern in some of the questions of folks who are saying, hey, you've got an annealing quantum computer, you've got a gate quantum computer, are they going to be sharing quantum information? Are they going to be exchanging pulses with one another? And so we're just as excited and interested by the possibilities of bringing the two technologies forward as you are. And the interesting thing is that Andrew King gave a great presentation at the Qubits User Group Conference about our ability to operate our systems in some new operating regimes at really high speeds. And so, what's significant about gate model operation is that you have a lot of control over the states of the qubits, and you're going to use that in order to help you with information processing. With quantum annealing, you're relaxing some of that control, and that's allowing you to build larger scale systems and help you with optimization problems. However, in Andrew's work, what we're seeing is there's actually a regime where we're operating our systems that we're seeing now, where 1,800 of our qubits are operating coherently, and that's the kind of operations that are happening in gate model systems. So we're going to focus on trying to bring these technologies forward for you to be able to use and leverage. But as the only provider in the world that's doing both annealing and gate, we're also going to be able to leverage a whole host of other interesting technological advancements that will become possible as our quantum annealers become more coherent with coherent operating ranges, and we have a lot of insight into coherent sets of qubits and cliques and interactions and how those can contribute. And maybe there's going to be ways that those interact or hybridize themselves that we can't even expect today, which I think is really exciting.
Thanks, Murray, for that context. And there's absolutely themes and patterns in these questions. And so it's really interesting to see that sort of accumulation of knowledge, and we hope we're answering them. And there's more resources in the chat to check out and dig deeper into some of this. And again, the Qubits talks are accessible via the link. You kind of register for the event, even though it's past, and then you can jump in there and check out all the great content. Those were the majority of the questions. A lot of them were answered as well by our team of experts here in the chat box or in the Q&A box. So again, thank you everybody for joining, and we will talk to you soon. And thanks, Mark and Murray, for presenting, and everybody here today for joining. And we look forward to continuing the conversation.
It's a pleasure. Thanks, everyone.
Yeah, thanks a lot.